Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 46. In this lecture, we'll discuss the kinetic theory of gases. This topic is covered in Chapter 21 of our textbook by Sir and Jouett. Before getting into the physics for this lecture, I want to tell you a little bit about the history of the subject that we're studying. What we've been studying over the last few lectures is known as thermodynamics. Thermodynamics is the study of how heat and temperature affect the behavior of substances. Another branch of physics is known as statistical mechanics, or StatMech, as it's referred to by physics majors. StatMech is the study of the motion of a large number of particles. As the name suggests, StatMech uses the laws of mechanics, such as Newton's laws of motion and conservation of momentum, to study the behavior or the motion of a very large number of particles. Here we're not talking about 10 or 15 particles. Here we're talking about trillions, or an Avogadro number of particles. Since the number of particles is enormous, we will often talk about the average properties of those particles as opposed to their individual properties. Now, for a long time, these two branches of physics seemed like two distinct topics. However, after the 1890s, it became increasingly obvious that fluids are made of discrete units, such as atoms or molecules. So prior to the 1890s, the atomic theory of matter had not yet been established, which means that many prominent physicists often thought of a substance like water as being infinitely divisible. Today we know that's not true. Given a quantity of water, you can certainly divide it into smaller and smaller and smaller quantities down to the level of a single H2O molecule. From that point on, you can no longer divide water into smaller quantities. You can certainly divide an H2O molecule into separate hydrogen and oxygen atoms, but then the resulting substances no longer have any of the properties that we normally associate with water. So we say that water is not infinitely divisible. This meant that many of the substances that people were studying in thermodynamics are really just made up of a large number of particles, and that those fluids can now be studied using techniques from statistical mechanics. In fact, thermodynamics was gradually replaced by statistical mechanics, and in this lecture, I want to show you essentially how that's done. We'll use the ideal gas model as our primary example, and we'll use techniques from statistical mechanics to describe the thermodynamic properties of an ideal gas. So our goal in this lecture is to use the laws of mechanics combined with a few facts from statistics to calculate the thermodynamic properties of an ideal gas. So ultimately, we'd like to be able to calculate, for example, the pressure or the temperature of an ideal gas based on the mechanical properties of the particles inside that gas. To that end, consider n particles of an ideal gas, each with mass m, in a cubical box with volume V equals d cubed. So imagine we have a cubical box with sides of length d, and imagine n identical particles inside that box. Here I'm showing you just one of those particles. This particle has mass m and it's moving in some random direction with velocity v. A little more precisely, let v sub I denote the velocity of the ith particle. So this could be the 5th particle, or the 7th particle, or the 700th particle. V sub I will denote the velocity of that particle. Now, velocity, of course, is a vector, so it will have an x, y, and z components. Here, I'm showing you just the x component of the velocity of one of those n particles inside the box. Now, since this particle has some mass and some velocity, it also has some momentum. Remember, momentum is simply mass times velocity. So we'll use p sub I to denote the momentum of the ith particle. Now this particle is moving around, and occasionally it will hit one of the walls of this box, And in that collision, it will exert some force on that wall. So let F sub I on W denote the force of the ith particle on that wall in a collision. Our goal will be to calculate the pressure and temperature of this collection of n identical particles based on simple mechanical properties like the mass and velocity of this particle. So now we'll carry out a rather long series of calculations that will culminate in a nice expression for the pressure of the ideal gas in terms of the mechanical properties that we just described. We'll concentrate on a single particle colliding with a single wall at first. What we're interested in is the force that the particle exerts on the wall. To calculate that force, we'll want to calculate the change in the momentum of that particle. Now recall that momentum is mass times velocity. So the momentum of the ith particle in the x direction can be expressed as mass times velocity of the ith particle in the x direction. Note that in this context, the subscript I labels the particles. It does not stand for initial. Now what we're really interested in is the change in the momentum of that particle in the x direction, and we can express that as follows: mass times velocity of the ith particle in the x direction after the collision minus the velocity of that same particle in the same direction before the collision. Now we are talking about atomic collisions here. These atomic collisions don't really make much sound or create much deformation, so they are elastic collisions. What that means is that the collision between a wall and a particle basically conserves kinetic energy. More importantly, what that means is that the speed of the particle before the collision is equal to the speed of the particle after the collision. For example, if a particle was moving with a speed of 10 meters per second in the positive x direction before the collision, then after the collision, it's going to be moving with the same speed of 10 meters per second, but in the negative x direction. So the speed after and before are equal, however, the directions are different. What that means is that the final velocity minus the initial velocity is basically minus twice the initial velocity. So we can say that the change in the momentum of the ith particle in the x direction is equal to minus 2m v sub ix. Now what we're really interested in is in the force, and we were just talking about how the velocity of a particle changes. The velocity of the particle changes because the wall exerts a force on it. Remember, a change in velocity is equivalent to acceleration, and acceleration is brought about by forces. So it's the force of the wall on the ith particle that causes its momentum and its velocity to change. We know from our mechanics course that force can be expressed as the derivative of momentum with respect to time. So the force that the wall exerts on that one particle in that one collision is equal to the change in the momentum of that particle divided by the time required for one collision. Here, delta t is a very, very, very short period of time on the order of nanoseconds that's required for a single atom to collide and bounce off of a wall. Now, what we're really interested in is the force of the particle on the wall. We know that according to Newton's third law of motion, for every action, there's an equal but opposite reaction. What that means is that the force of the ith particle on the wall is basically equal in magnitude to the force of the wall on that particle, but in the opposite direction. That's indicated by the negative sign here. We know what the change in momentum is. We can substitute it in this expression, and then we can take this expression and substitute it down here. And finally, we find that the force that the particle exerts on the wall in a single collision is 2m vix divided by delta t. Now, so far we've been talking about the collision of one particle with one wall. Of course, that one particle will collide with that same wall many times. So what we're really interested in is in the average force of that particle after many collisions with that same wall. To calculate that average force, we'll take the force of one collision multiplied by the time required for one collision and divided by the time between two collisions. Note here that we're using a slightly new notation. When we place a bar over a quantity, we're talking about the average of that quantity. So this is a common notation from statistics. Also note that we're assuming that the time between two consecutive collisions with the same wall is 2d divided by Vix. So here we're imagining that, for example, a particle collides with the wall at t equals 0, and then it moves away from the wall, travels the length of the box to the opposing wall, bounces off that wall, and comes back to the original wall. The total distance traveled for the round trip will be 2d, and that distance will be traveled with this speed. So if we divide the distance by the speed, we find the time that it requires between two consecutive collisions. Now we already have an expression for the force of the ith particle on the wall. If we substitute this expression in here, what we find is that the average force of the ith particle on a single wall is mv squared over d. Now these last two steps require some further explanation. Here we're using some important concepts from statistics, so I want to pause and over the next two slides explain a few facts from statistics before continuing this calculation. Before continuing with our calculations, we need to take a detour to learn a few facts about statistics. Specifically, we want to learn a little more about averages. The average of a discrete variable f sub I can be calculated using this equation here. So here we're imagining some discrete variable f with distinct values which we are labeling using the index I. So we have values f sub 1, f sub 2, all the way to f sub n, where n labels the total number of values that we want to average. To calculate the average value, we add all of those values together, and then we divide by the number of numbers that we just added, and that gives us the average of that variable. This is the procedure that you would follow if you wanted to calculate, for example, your average score on 3 midterms with equal weights. You would take your score for the first midterm, add it to your score for the second midterm, add it to your score for the third midterm, and then divide by 3 because we're talking about 3 values here that are being averaged. Notice that we're using an overbar to indicate average. So this is a common notation. A line over a quantity means the average value for that quantity. Now, so far we've been talking about a discrete variable. A discrete variable is basically a set of values that can be indexed using the integers. So we can clearly talk about the first value and the second value and the third value. But one might also be interested in the average of a continuous variable, a variable f that depends on a continuous variable such as time. For example, you might be interested in the average temperature throughout the day. The temperature, for example, in your city depends on time in a continuous fashion. Or you might be interested in the average value of the speed of a car that is speeding up and slowing down. For a continuous variable, you calculate the average using this equation here. Notice the equation isn't very different, except instead of a summation, we're going to carry out an integration. The integration is going to be carried out over some period of time from 0 to capital T. So if you want to calculate the speed of a car, for example, over a 6-hour race, you would integrate the speed of that car as a function of time from 0 to 6 hours. Notice also that we're essentially dividing by the number of variables that we're adding. Of course, time here is a continuous variable, so we're not really dividing by the number of times, but by the duration of time. This is the procedure that you would follow if you wanted to calculate the average speed of an automobile during some time delta t. You would say that the average speed is equal to the integral of the speed as a function of time from t equals 0 to some final time, let's call it delta t. You would then write the velocity as dx dt. Then you would notice that dt and dt cancel. The integral of dx is just x. When you plug in the limits of integration, after a few more steps, you will find that the average speed is delta x divided by delta t. So this is hopefully an expression that you're familiar with from your mechanics course. Deriving this expression is just an application of this averaging formula for a continuous variable. On the previous slide, I was talking about the average of some arbitrary continuous variable. But what we're really interested in is the average of the forces that are exerted on the walls of that box filled with the ideal gas. To calculate that average, we're going to assume that force as a function of time can be described by a graph that roughly looks like the one shown here. So this is a graph of force versus time, and I'm imagining that at t equals 0, the particle collides with a wall, and in that collision, it exerts a force that I'm going to call force of the ith particle on the wall, and that force will last a very short period of time, and then it basically stops once the particle has bounced or rebounded from the wall. Then there is no force on that wall, at least due to that one particle, until the wall completes a round trip. When the particle comes, again, it collides with that same wall, and for a very short period of time, we'll call it delta t, it exerts a force on the wall, and then once it's bounced off, again, the force becomes 0 until it returns to that wall sometime later and again exerts a force. So this graph describes the force that one particle exerts on one wall. What we're interested in is calculating the average force that the one particle exerts on the one wall. Based on our discussion from the previous slide, the average force is equal to the integral of the force as a function of time from 0 to t, and then we'll divide by the total time interval. Now, from your calculus class, hopefully you'll remember that the integral of a function is basically the area under the graph of that function. So when I say integrate f with respect to t, I'm basically asking you to calculate the area under this function, and the area under this function essentially ends up being this area here because the function everywhere else is essentially 0. So now we can calculate this average relatively easily. We can say that the average force is equal to the height of this rectangle times the width of this rectangle. So force of the ith particle on W is the height times the width, which is delta t. And then we're going to divide it by the total time interval. I'm just going to consider one cycle here. That time interval is the time it takes for the particle to complete a round trip and collide with the wall again. That's just 2d divided by Vix. Now, through a series of calculations, we found the force that one particle exerts on the wall to be 2mv divided by delta t. And now you can see that this expression simplifies dramatically. This delta t cancels this delta t, this 2 cancels this 2. This Vix can be combined with this Vix, and we found that on the average, the force that one particle exerts on one wall is mass times velocity squared divided by distance. Now that we know a little more about statistics, we can return to our calculations. Up until now, we've been talking about the average force that one particle exerts on the wall, but of course that's not enough. What we're really interested in is in the force that all particles exert on the wall. So we want to calculate the average net force on that wall. To calculate that, we'll have to sum the average force that the ith particle exerts on the wall. This summation will have to be carried over all n particles. Now, in the previous slide, we calculated that the force that one particle exerts on the wall on average is equal to mv squared over d. M is the mass of a single particle. We're assuming all particles have the same mass, so that's a constant that we can bring out of the summation. D, of course, is the length of one side of the box. That's also a constant, and we can bring that out of the summation. And so we find that the average net force on that one wall is mass divided by D times the sum of the velocities squared. Now, different particles are doing different things, but on average, these particles are essentially the same. So when I ask you to sum n values of v squared, that's essentially the same thing as multiplying v squared by n. A little more precisely, I can say that the sum of v squared for the individual particles is equal to n, that's the number of particles, times the average value of v squared in the x direction. Here I'm using the discrete definition of averages. Now notice up until now we've been imagining that the particle is moving only in the x direction, but of course that's not necessarily true. We just basically chose the x direction because it was convenient, but in general these particles are moving in the x direction, in the y direction, and in the z direction with equal likelihood. So what we really want to talk about is not just the x component of velocity, but just the speed, including the x, the y, and the z components. Now, according to the three-dimensional Pythagorean theorem, we can calculate the square of the magnitude of the velocity vector by adding the squares of the components of that vector. Since the box is a cube and the x, the y, and the z directions are all equally likely, we can say that these three numbers or three terms in the summation are basically equal to each other. We can say that on the average, the y velocity of the particles is equal to the x velocity of the particles. And on the average, their z velocity is also equal to their x velocity. So we can say that the average of the speed squared is simply 3 times the average of the x component squared. So I'm going to replace v sub x with v, and then I'm going to multiply it by 1/3. This is finally the expression that we want. This expression allows us to finally calculate the pressure of the ideal gas. Recall that pressure is force divided by area. The area is going to be the area of a single wall, which is d squared, and the force, of course, is this net average force that we've calculated. If we take this expression here, plugging in for the net force here, we find that the pressure of the gas is equal to 2/3 times the number of particles divided by the volume of the box times 1/2 mv squared. The v squared you have to be a little careful with. Notice that there's a bar over it. The bar indicates that we're not talking about just the speed of a single particle. We're talking about the average of the squares of the speeds of all the particles. Finally, this is the expression that we want. Notice that this expression tells us what the pressure of the gas is in terms of very basic mechanical properties like the mass of a single particle and the speed of the particles. So what we have accomplished so far is to express the pressure of an ideal gas in terms of its mechanical properties. We can do the same thing for the temperature of the ideal gas. Recall that an ideal gas obeys the ideal gas law, which says pressure times the volume of the gas is equal to the number of particles times the Boltzmann constant times the temperature of the gas. Now, we also just found an expression for pressure. Substituting that expression here, we find that pressure times volume is 2/3 times the number of particles times 1/2 mv squared. Now, equating these two expressions together, we find that the temperature of the gas is equal to 2 divided by 3 times the Boltzmann constant times 1/2 mv squared. Again, note that this v squared here is really the average of the square of the speeds of all the particles. So we now have two expressions, one for pressure and one for temperature of an ideal gas. in terms of basic mechanical properties. You don't need to memorize every detailed step of the rather lengthy series of calculations that we just carried out. However, you do need to be very familiar with the final results. In essence, the question that we've been trying to answer is the following. Consider n particles of an ideal gas, each with mass m in a box with volume v. Suppose the mean speed squared of the particles is given. Based on this information, what are the pressure and temperature of this ideal gas? The answers are exactly the two expressions that we just derived. Incidentally, you may have noticed that this 2 here can be canceled out with this 2 here. However, I prefer not to do that. And the reason is that hopefully 1/2 mv squared reminds you of something you've seen before. 1/2 mv squared is essentially the kinetic energy of the particle. What that means is that we can express the pressure of the ideal gas as 2/3 times the number of particles divided by the volume of the gas times the average kinetic energy of a single particle. The temperature of the ideal gas can also be expressed as 2 divided by 3 kb times the average kinetic energy of a single particle. This is important because it establishes a clear relationship between thermodynamic parameters like P and T and mechanical parameters like kinetic energy. It also tells us that when the temperature of some material increases, we're essentially increasing the average kinetic energy of the particles of that material. Incidentally, note that if we started with these two expressions, P and T would automatically satisfy the ideal gas law. Let's end this lecture with a practice problem. The average molar mass of dry air is 28.97 grams per mole. Approximately how fast do air molecules move at a temperature of 25 degrees Celsius? You may need the following constants. I've mentioned before that when you heat something up, you're basically making the molecules or atoms of that substance move faster. We're now in a position to calculate the actual speed of the molecules given their temperature. From our kinetic theory of gases, we know that the temperature can be expressed as follows. By rearranging this expression, we find that the average square speed is equal to 3 times the Boltzmann constant times the temperature in Kelvin divided by mass of a single particle. Taking the square root of both sides of this equation, we find that the average speed can be expressed approximately as the square root of 3 kBt divided by mass. Now, lowercase m is the mass of a single particle. What we're given in the problem is the mass of 1 mole of air. 1 mole of air, of course, is an Avogadro number of air molecules. So we need to take the mass, convert it to kilograms, and then divide by Avogadro's number to find the mass of a single air molecule. Plugging those numbers in, we find that the average speed of an air molecule is approximately equal to 506.5 meters per second, which is quite fast. Converted to miles per hour, you find that the average speed of air molecules is 1,133 miles per hour. Now, it turns out this is a slight overestimation. The overestimation is coming in part from the fact that we're ignoring that air consists of different molecules with different masses. But more importantly, here we are assuming that the square root of the average of the speed squared is simply equal to the average speed, and that's not entirely true. However, this number does give us a very good approximation to the actual speed of air molecules. And that is the end of this lecture. Thank you for your attention.